All right, welcome back to the online causal inference seminar. Today we're excited to have Wooseok Ha from the Korea Advanced Institute of Science and Technology, who will talk about domain adaptation. So when few labeled target data suffice, a theory of semi-supervised domain adaptation via fine-tuning from multiple adaptive start. The discussant today will be Jason Klusowski. We're very excited. Questions today will be handled by Emma. Emma, do you want to say a few words?
Yes, sure. Hi, everyone. So as always, we will be handling the questions through the Q&A, not through the chat. So please submit your questions through the Q&A. We are pleased to say that Wooseok has his collaborator, Yuan Chen from ETH, to answer questions. So all your questions will be answered in the best way possible. But yes, please don't hesitate to to ask questions as soon as they come up, because it takes a while to get through all the questions. That's it. Thank you so much. And Wooseok, you can take it away.
Okay. Okay, so can everyone see my screen? Cool. Okay. So thank you for the introduction, and thank you so much for all the organizers for having me here. It's my great honors to present my recent work in this online causal inference seminar. Okay, so this is a joint work with Professor Yuan Chen from ETH Zurich. It's always great pleasures and really inspiring to work with him. Okay, so here I will first start with some motivations and problem setup for the domain adaptations. And then I will talk about some semi-supervised domain adaptations under linear structural causal models. And then we develop some new fine-tuning algorithms under different interventions. And I will conclude with some simulation results. Okay, so I believe that all of you must be familiar with the distribution shift. So this is a very famous the Chameleon 17 dataset. So here we are given some image of the tissues, and the goal is to predict whether there is any tumor tissue in the center of the image. And here we train the models from some of the training hospitals. And then we want to generalize our models to the images from the new hospital, where this new hospital is not in the training hospitals. And here we have some distribution shifts between the different hospitals because they have different protocols in data collection and data processing, which actually cause the distribution shift. So this is the so in the top left plot, this is a well-known the wild benchmark for the distribution shift. So here, the authors, the Ko et al., they collect some real-world data sets with domain shifts. And then Chameleon 17 is one of these benchmark data. And they actually trained the empirical risk minimization, so ERM, on Chameleon 17. And they found that the ERM actually suffers about like 23% performance drop from in distribution to out of distributions on this Chameleon 17 dataset. And they also try this across different data sets in this benchmark. And they also found a similar generalization gaps between the in distribution and out of distribution performance in this benchmark. And people also found more examples where the machine learning models are quite not good at the distribution shift. So here is another examples where in Redford et al. In 2021, they just have some ImageNet trained models, and then they evaluate in different variations of the ImageNet data sets, and under some domain shifts like style or some sketch, they found that the performance also drops a lot. And in in computer visions, they also found that the image models like CNNs, they have some strong bias towards the texture. So if the image, the CNNs have an input with this the image on the left, then they can correctly predict this as the elephant. And in the middle, if they take the cat image as an input, they can correctly predict it as a cat. But if the model sees the image which has the shape of the cat with the different textures, then they classify it as an elephant. So which shows that the model has some strong bias towards the textures. And if there is some shift in the textures in the in your target distributions, then model can fail. Okay, so the domain adaptation is the learning problem to address this distribution shift. So the setup is as follows. So we have some source data from many environments where M can be either 1 or bigger than 1. And for the source data sets, we observe both the labeled and unlabeled data. And we use the superscript M to denote the index of the environment. And we also use the subscript U to denote the unlabeled data. So we have this the source data from M environment. And for the target data, we observe the data set from new environment, where again, we observe the labeled and unlabeled data sets IID from some distribution. And we use the superscript 0 to denote the index of the target environment. And here, our goal is to train the model F that minimize the target risk, which is just given in this way. And in domain adaptations, there are different the settings. So the unsupervised domain adaptation, or the UDA, is a setting where we have the unlabeled target data, but we don't observe any labeled target data. And in domain generalizations, we don't observe any of the labeled and unlabeled target data. So we only observe the source data and then use this data to build a model. And in semi-supervised domain adaptations, or SSDA, we observe both the labeled and unlabeled target data, but for the labeled target samples, we only have a very small number of the samples observed. Okay, so then a natural question in the domain adaptation is whether we can beat some simple baselines, such as OLS pool or OLS star, where the OLS pool is just a simple model that just combines all the source data and just train the models like using ERM. And we can think of this as a natural baseline for the unsupervised domain adaptations or domain generalizations when we don't use any target labels. And OLS star is another natural baseline, especially in SSDA, when we just directly train the models on the limited labeled target samples. So this is another natural baseline. And people have also developed more advanced unsupervised domain adaptations and domain generalization methods. So one of the most popular algorithms is the DIP, or the domain invariant projections. So here, the model F is just some composition of the function G and then the phi. So you can think of the phi as extracting some middle layer features from the input X. So phi is some feature extractor, and then G is the prediction model that is based on the features. So in DIP, what they find the G and phi by minimizing the source risk with the constraint that in the middle layer features, the distributions of the source and target they are close, or they are just equal to 0. So here the D is the distributional distance, such as MMD or Wasserstein or some adversarial net. So the idea is that the DIP assumes some existence of the common features, and they extract these common features between source and target covariates by putting this the invariance constraint. And the conditional invariant penalty, or CIP, is another popular algorithms in domain generalizations, where here they, instead of using the target covariates, they use the multiple source domains. So model F is a composition of the G and phi. And again, the phi is the feature extractor and G is the predictors based on the features. And then G and phi is trained to minimize the combined source errors across multiple source environments, with a constraint that the conditional distribution of the features given Y is the same across all the environments. So here, the hope is that if the features are conditionally invariant across multiple source environments, then we hope that this conditional invariance is also true for the target domain. So the features phi which satisfy this conditional invariance between source and target, this is called the conditionally invariant components in the literatures, or CICs. And under some strong assumptions, we can also show that these CICs are identifiable whenever we have enough number of the source environment. Okay, so these DIP and CIP algorithms have shown many empirical success, but we don't use any target labels in these algorithms. So this makes these algorithms quite unreliable in many scenarios. So one example is that if the data generation is causal, in the sense that we first generate the x, and the y is generated by some functions of the x, then in this case, it's known that DIP is no better than a simple OLS estimator based on the source. So the intuition is that the generations of the covariance x and then the generation of the y given x, they are just separate. So even if we have many target covariates, this covariate information does not give any information about the y given x. So this kind of idea was discussed first in this Shokov et al. In 2012, and then this Yuan-Si Chen and Peter Buhlmann, they brought this idea to the domain adaptation setting. Also, another well-known scenario for the failure of the DIP is when there exists some label flipping features. So this is an example of the data set from the colored MNIST. So you have the source and target data, where the source and target have digits 4 and 5 with the different colors. So DIP just match the marginal distributions of the covariates. So if they can either extract the shape features or the color features to match the source and targets. So in case they extract the color features, the models trained with the source data can fail in the target distributions because the green features in source correspond to the label 5, digit 5 in the target. So when we have this kind of label flipping features, we cannot guarantee that DIP algorithms will always succeed. And also the CIP algorithm is also quite overly conservative, because in the CIP, we try to find some conditionally invariant features across multiple source environments. So which means that we have to throw away a lot of information to make sure that the features are invariant across many environments, so which often leads to suboptimal performance on the target distribution. So the semi-supervised domain adaptation is a more practical setting for domain adaptations, where we not only use the source and unlabeled data, but we also use the limited labeled target data. So if we define the target access risk in this way, just for the target risk, access risk of the model F is the difference of the risk of the F and then the optimal risk, optimal target risk. If we use this as the measurable performance for the algorithms, then by taking advantage of the limited target data, we want the target access risk of the SSDA to be lower than that of the target-only methods or the unsupervised domain adaptation or domain generalization methods. So not only that, we want this access risk to be lower than these baseline algorithms, we can be more ambitious, and we can also ask whether the SSDA can achieve the minimax-optimal rate. So the minimax, the target access risk can be just defined in a similar way to the classical setting, where we just have the mean over the estimator F and then supremum over some distribution class. And this for each distribution in the distribution class is now the distribution over all the source and target data points, combining both the labeled and unlabeled data. And here the minimum is taken over all the estimator from some function class F. And for these papers, we consider the linear function class for simplicity. Okay, so then we can have the following questions. Can you show that this SSDA can provably outperforms the baseline algorithms, such as the target-only methods that only use the target data for predictions, or the UDA or DG methods? And also, what type of the structures in distribution shifts SSDA can use for most efficient use of the target labels, or in other words, whether we can SSDA can achieve the minimax optimality. And our contributions are the following. We introduced some new SSDA methods that apply the fine-tuning strategies tailored to the different types of the distribution shift. And when this the type of the distribution shift is vaguely known, then we just combine these new SSDA methods with the model selections, which we name it as Multi Adaptive-Start FineTuning, or MASFT. Okay, so maybe I'll pause here and then just take some questions if there is any.
Hi, Wooseok. At the moment, we don't have questions, but I'd like to encourage everyone to please submit your questions to the Q&A. And that's it. So please continue.
Okay, cool. So, okay, so here for the semi-supervised domain adaptations, we want to analyze this from the structural causal model framework. So I believe the audience here must know these structural causal models better than me. But these SCMs, structural causal models, describe the data generating process through some causal relationships between variables. And these SCMs has been used to model distribution shift as interventions on the data generating process. And this approach has been established by a group of researchers in ETH Zurich and also Stanford. And in our settings, SSDA, these structural causal models they are just the data generation models for both the source and target data. And we use these data generation models to prove some guarantees for the algorithms, but we don't actually need to know the SCMs to run the method. Okay, so here we consider the anti-causal linear structural causal models. So for the source and targets, the data generation is given in this way. So X and Y follows the structural equation models. And here the Y is the root node in the anti-causal models. So first, Y is generated from some distribution, and then given Y, and X is generated following these linear structural equation models, where the matrix B encodes the causal relations between the covariates and this the vector B. We call this anti-causal weight vector. B is the effect of the Y on the covariance X. And this anti-causal data generation models is common in many machine learning data sets. So for instance, in medical diagnosis, let's say if the Y is the COVID-19 infection, and let's say X is the lung fields in chest X-rays or some symptoms of the COVID, then this actually has the anti-causal data generation process. And also in the image recognitions, if the Y is the handwritten digits, let's say, then and given these digits, it generates some X, which is a two-dimensional image of the digit. Okay, so in this anti-causal linear structural equation models, we can think of the different types of the distribution shifts. And here we consider three different types of the distribution shifts. So the sparse connectivity interventions, the confounded additive interventions, and then the anti-causal weight interventions. So in the sparse connectivity interventions, this matrix B between the source and target, they change, and the perturbation occurs in R columns among the D many columns in B matrix. And in the confounded additive interventions, the noise distribution, they change between the source and target because of some low dimensional unobserved compounder. And in the anti-causal weight interventions, we assume that this anti-causal weight vector B, they change between the source and target in some low dimensional subspace. So let me just briefly compare our approach with the previous approaches in the literature. So existing works in these literatures, they assume that the shift from the source to target, this shift occur directly in the regression coefficients to be estimated. And these literatures often, they are just often referred to as the transfer learning. So for instance, in the sparse regression models, Y is given by the X times beta plus some noise, where beta is sparse. And then in the target, maybe there is some shift in the coefficients beta, maybe in some sparse directions. And here, our approach is slightly different, and we take a different viewpoint by just assuming that the distribution shift arise as interventions in the data generating process. Eventually, this shift influence model parameters to be estimated. But if when in the situations where it's more intuitive to modeling the distribution shift at the level of data generations, then our approach can be more tractable compared to the previous approach, where they just directly model the shift in the parameters to be estimated. Okay, so because we consider the linear structural equation models, we consider the linear function class. And here we first define the oracle estimator, which is just the population ORS estimator on the target distributions, which we just write it as beta star. Then first, if we only use the target data for the predictions, we have this the following the minimax lower bound. So let's say our data follows the anti-causal linear structural causal models. Then the excess risk of the your excess risk can be over your estimators, where the excess risk in these linear models is just the difference between your estimator and then your oracle estimator, varied by the covariance matrix. So this excess risk is always lower bounded by the d over n, where d is the dimensions of the covariance, and then n0 is the number of the labeled target sample. So this rate is quite well known in classical linear regression setting. And what we show here is that even for the anti-causal settings with the unlabeled data, still it doesn't affect any classical minimax lower bound. And especially when the number of the labeled target sample is much smaller than the dimensions of the problem, then just by using the target data, both the labeled and unlabeled, they cannot reduce the excess risk below some constant. Okay, so now let me give you some two motivating examples so that how we can beat these target-only methods by using some additional source data. So the first example is the sparse connectivity perturbations. So here we have the source and target, which follows these causal diagrams. And the Y's, the labels are just some Gaussian distributions, and then the three covariates they are generated by these linear structure equation models. And here the perturbation is on the mechanisms of the x1 to x2 and x3. So in the source, these coefficients for the x1 is 2 and 2 here, and in the target domain, the coefficients for the x1 is -2 and -2. So in this case, we can see that even though there is the mechanism shift for the x1, if we look at the partial correlations between the x2 and y and x3 and y, they remain the same between the source and target, because the partial correlations look at the correlations after you remove the effect of the x1. So in other words, only the regression coefficients for the x1 change from the source to target. So if we compute the ORS source estimator on the source data, then the difference between the ORS estimator and then the oracle estimator must be sparse. So in SSDA, we only have the limited target labels. So the natural strategy is that we can just fine tune the ORS source in the sparse directions. And another example, the second example is the mean shift perturbation scenario. So here we have some y from, let's say, from some Gaussian distributions, and we again have some three covariates, and these covariates have some mean interventions. So in the source, the means of the x1, x2, x3 are all 1, and in the target domain, the means of the x1, x2, x3 are just -1, 0, and 1. So there is a shift of the mean between the source and target. And in this case, we can actually show that if we use the DIP algorithms with a mean matching penalty, where the distributional divergence is just the mean difference between the source and target, then this mean matching penalty gives you this constraint. So just make sure that the difference between the source and target covariance after you project to the by beta, they must be the same. And this DIP penalty is just trying to find the beta, which is orthogonal to the perturbation directions from source to target, which is just 2, 1, 0 vectors. So meaning that when you project the x to the beta directions, they can capture these 2-dimensional common features between the source and target. And we are only left with 1 dimensions. And just by using the target labels, we can just fine-tune this DIP estimator in this 1-dimensional subspace. Okay, so these are just the main ideas about how we can use the target labels when there is some structures in distribution shift. And in particular, just I want to emphasize that for the efficient use of the target labels, it really depends on the type of the distribution shift. Okay, so now let's make this idea more concrete. So in the next few slides, we'll just make this more precise and more quantitative. So let me first consider the compounded additive shift intervention, or the CA shift intervention, where we have the source and target data generations given by these linear structure equation models. And the distribution shift is, we have some distribution shifts in the noise distribution. And in particular, they are perturbed by some hidden confounders. So in the source distributions, the epsilon x and epsilon y are from some distributions. And in the target domain, let's say we have some psi x and psi y. They are from the same distribution as the source noise distributions. And we have some additional confounder z, which is r-dimensional random vectors that acts additively to the target noise. So our target noise for the x and y are given by this. And under these CA shift interventions, if we make the source and unlabeled target sample size, they grow to infinite, then we can show that the minimax access risk is always lower bounded by R over N0, where R is the dimensions of these confounders that induce the distribution shift, and N0 is the number of the labeled target samples. Okay, and the next question is, okay, so we have this lower bound. So how can we achieve this lower bound? So we developed some new fine-tuning algorithms in these CA shift interventions. So here we use the DIP algorithms with the covariance matching penalty. So the DIP, so which is just given by this. The DIP estimator in this case is just the minimizers of the source risk under the constraint that the source and target covariance matrix must be matched. And under our data generations, the CA shift interventions, the difference between the target and source covariance matrix is just a passive semi-definite with a rank R. And we can actually show that under this constraint, the source and target distributions, the source and target data are just have the same distributions. So we can equivalently write this original DIP formulation as these formulations on the right, where the DIP is given by the minimizers of the target risk with the same constraint. So if we just look at this, the formulations, DIP estimator is just the minimizers of the target risk with additional constraint where this constraint is R-dimensional in R dimensions. So if we implement the DIP, then we only lose the R dimensions compared to the Oracle estimator. So if the here is what just this is just what I just explained. So DIP is just lives in the some orthogonal complement of the eigenspace of the difference between the covariance matrices. Let me just write this by some the span of the Q, where Q is the basis matrix for this orthogonal complement. Then this has a dimensions d minus r. Then because they only lose the R dimensions, what we can do is we can just fine tune DIP in the directions orthogonal to the Q, which is just the R dimensional subspace. So this is the main idea. And we can just use this idea to formulate the fine tuning the DIP estimator. So the estimator is just trying to minimize trying to fine tune the beta on the labeled target samples with the constraint that on the Q directions, they don't make any updates, and we only fine tune the beta in the orthogonal directions of the Q. And if we define the fine tuning DIP estimators in this way, then we can show that the target excess risk of this estimator is upper bounded by these terms, where the important part is this first term, which is given by the R over N, and with some additional terms. And if we have a large source and unlabeled sample size, then these terms is just the small. So we can show that the fine-tuning DIP estimator, they achieve the minimax rate. Okay, now let's consider the second intervention scenario, where we have some sparse connectivity shift intervention. So again, the source and target have this follows this linear structure equation model, where now the shift occurs in the connectivity matrix B, and specifically the source and target B matrix change in R many columns. So in this case, we can extend the previous discussion in the TOEIC example, and we can show that the source and target, the OLS estimators on the source and the Oracle estimator in the target, the difference between these two are R sparse, where these non-zero coefficients appear in the intervened covariance. So again, in this shift intervention scenario, if we grow the source and unlabeled target sample size to infinite, the minimax excess risk is lower bounded by R over N, where R is the perturbations of the columns of the B matrix, and then N0 is the number of the labeled target samples. And because
sorry to interrupt, I just want to remind you of the time. You have around 7 to 8 minutes left.
Okay, thanks. Yeah, so I'll just speed up. Okay, so now we have the difference between the OLS source and then Oracle estimator is sparse. We can just use the idea of the sparse regression, so we can fine tune the beta on the labeled target samples with this L1M constraint. Then we can show that under some mild conditions, the target excess risk of this estimator is bounded by some two terms, where the first term is attributed by this fine-tuning on the labeled target samples, which is given by R over N with some additional log factors. And then the second term is just the error that appears by estimating the OLS estimator by the source data. And when the source sample size is large enough, we can ignore this second term. So again, this fine-tuning OLS estimator is minimax-optimal. And lastly, we consider this anti-causal weight shift interventions, or the AW shift intervention. Again, we have the source and target data follow these linear structure equation models, and then the perturbation is on this anti-causal weight vector B. And we actually make an assumption that the perturbation directions from source to target, which is B0 minus B1, they can be spanned by the perturbation directions observed in the source domains. And these perturbation directions they live in the low dimensional subspace with dimension R, so they cannot span the whole space. And these AW shift interventions, if we allow to use the unlabeled target samples, the problems becomes quite easy. So here in this work, we also assume that in this intervention scenario, we don't allow to use the unlabeled target data. So in this case, the minimax access risk can be lower bounded by R over N again. And then just to achieve this rate, we consider the CIP estimator with a mean matching penalty. So the intuition is pretty similar to the DIP estimator, but what I want to emphasize here is that the CIP estimator, they can find some D minus R dimensional invariant features, so that we can only fine tune this CIP in the R dimensional the directions. So this is given by our estimator here. And just to note that this formulation is when we use the unlabeled target samples to estimate the covariance matrix, target covariance matrix. And we can also, if we are not allowed to use the target unlabeled samples, we can still propose a variation of this fine-tuning CIP estimator. And then we can show that under some conditions, the target access risk of this fine-tuning CIP estimator is also upper bounded by the R over N plus some terms, which goes away if the source sample size is large enough. So we can also show that this is achieve the minimax optimal rate. Okay, so let me just briefly talk about the multi-adaptive-start fine-tuning algorithms. So here, so far, we show that this effective fine-tuning must be tailor-made for different types of interventions. But in practice, the type of intervention is unknown. So in this case, we can just try different fine-tuning algorithms with a multiple adaptive starts, and then we can do the model selection. So the intuition is that this is possible because the model selection is quite cheap. So if we try the fine-tuning, let's say L different models, then we only need the log L many labeled target data to select the best models among these L fine-tuned candidates. So our multi-adaptive-start fine-tuning algorithms is implemented in 3 steps. In the first, we just train L many, let's say the DIP or CIP or the OLS estimators on the source and unlabeled target data. And then we can just fine tune each of them using the labeled target data. And then finally, we have a holdout validation labeled target data. Use this to select the model with the lowest validation risk. And just combining our previous theorems for individual fine-tuning methods with the model selection result, then we can also show that this MASFT, they can achieve the same rates as the individual SSDA methods with additional error terms, which only depends on log factors. This is just a very small error terms. Okay, so I will just keep the simulation result. We just show that we just try different data generation models, and we can show that our fine-tuning algorithms can have better performance compared to the baseline algorithms. So we have some results in the paper, so please take a look at the papers if you are interested. So let me just summarize. So we proposed some theoretical framework for the semi-supervised domain adaptation, and we also show that the fine-tuning must be tailor-made for the different type of the interventions in your data generations. In particular, this says that there is no universal fine-tuning algorithm in SSDA. And then we show that the fine-tuning from these UDA algorithms can be minimax-optimal under some linear structural causal models. And our MASFT algorithms motivates the development of the new UDA methods and new fine-tuning strategies. And we have many open and challenging questions. So let's say how can we extend beyond the linear structural causal models and linear function class? And how can we develop some efficient fine-tuning in the latent feature space? And also, how can we understand the relationship between the fine-tuning dynamics and then domain adaptation assumptions? Okay, so thank you for your attention.
Thanks.
Thank you. So, there is one question in the Q&A, so maybe we can quickly get through it before the discussion. So the question is, would it be difficult to go beyond linearity of structural causal models to nonlinear models?
That's a very interesting question. So we also try to think about how we can extend beyond the linear structural equation models. One difficulty is that our algorithms is based on the UDA algorithms like DIP or CIP algorithms. But the main challenge is that for the beyond the linear structural equation models, even for these UDA algorithms, it's not theoretically well understood. And we can actually find that these DIP algorithms cannot identify the correct invariant features. So if we want to develop our framework beyond the linear case, then we have to first try to get some nice theory about the UDA algorithms first.
Great, thank you. Yeah, so yeah, thanks again for the nice talk. I think in the interest of time, let's switch over to Jason's discussion. Jason, please take us away.
Sure. All right. So can you see my screen? Let me just do full screen. You can see my screen? It's good? Okay, awesome. So yeah, thanks a lot, Wooseok, for the wonderful talk, and thanks to Dominic and to Aditya for the invitation to discuss the paper. It really is a pleasure to be able to do this. So I just want to kind of provide a little bit of a summary, I guess, of the talk and the problem, and then conclude with just a few of my own thoughts. They're actually very relevant already to the discussion. So okay, so what is the paper about? Well, the paper is trying to adapt using source data, unlabeled target data, but then with constraint where you have few labeled target samples. So the setting here is you have a source distribution, you observe maybe a lot of data from that source distribution, but what you're really interested in is making inferences about the target distribution. But the caveat here is that you maybe only have a few labeled data, maybe if any at all, but then you also have many unlabeled data from the target domain. Okay, and so there's kind of a semi-supervised / transfer learning type of flavor, type of setting going on here, which makes it quite interesting. And so the challenge here, of course, is you want to balance these two sources in a way that optimally kind of aggregates or combines the two sources of data. I mean, if you're too source heavy, right? Especially if there's a large distribution shift, you're going to incur a very large amount of bias. If you're too target heavy, right, because you don't have a lot of data in the target domain, you might inflate your variance. And so the question kind of is how do you optimally balance those two different regimes? So the main modeling framework and setting that the paper explores are these so-called structural causal models, which I think are quite interesting. And so basically what these models allow you to do is to model causal relationships between the input parameters, or sorry, the input variables, as well as the relationships between the labels and then the covariates, the predictor variables themselves. Okay, and so the relevant quantities here that are going to capture different types of distribution shifts between the target and the source are going to be the capital B and the little b here. Okay, and I think as was discussed, the main reason, from what I understand, that they focused on these linear SCMs is due to the kind of the analytical tractability. Okay, and so kind of using this structural equation to model these relationships, the authors consider three different types of methods. So the method one is the confounded additive. So this is where the b's are the same and the little b's are the same. But then these errors are allowed to change or shift via some low dimensional confounder. Okay, and this is an unobserved confounder. Okay, and then method two is the little b's here are fixed, and the error distributions here are fixed or the same. But what is allowed to vary are the columns of these B matrices. And so here I'm abusing notation a little bit here, but what I really mean is just that in this case at most S, or I think in their notation at most R, of the columns of these B matrices differ. And so you have a type of sparsity assumption. And then the third is this anti-causal weight assumption, a shift assumption. And here the capital B's are the same, the laws of the errors are the same. And what really changes are the perturbations between the little b's, between the source and the target, in the perturbations of potential multiple source distributions. So I think the way I've written it here is maybe technically incorrect. These should actually be more in terms of perturbations. But and the assumption here is that these perturbations live in a low dimensional subspace. And so again, you have these very interesting structural assumptions on the way that these distribution shifts occur across the source and the targets. And again, it exploits this very nice crisp linear causal model. Okay, so the main theorem here, the main theoretical result, is that under these structural causal model assumptions, each matched method attains a minimax-optimal target risk. And the way that this is done is via a two-stage approach. So you first train an unsupervised domain adaptation method on the source plus the unlabeled target. And the way that this UDA, this unsupervised domain adaptation, is done is it exploits the invariance properties that come from the type of shift. And then the second stage is you do some fine tuning with the target labels that you have, although you don't have too many of them. And so in some sense, like the main kind of punchline of the methodology is that if you kind of start right, so in other words, you have the right UDA initialization, which corresponds to the right invariance from the type of distribution shift that you're assuming, that kind of matters more than actually having more labels, in fact. And so that's what's kind of interesting about the paper. So that as we saw in the talk, the rates depend on the type of shift, the tuning dimension, and of course the starting quality. And so all of these things determine the risk. Okay, and then I think this was briefly touched on at the end of the talk, which is, okay, what happens if the actual shift is unknown? So I said that, you know, what these earlier methods rely on is actually having the right start. So in other words, kind of knowing in advance what the right type of invariance, the right type of shift is, so that you can, you know, tailor your UDA to that. But what happens if you don't know it? And so now what the authors do is they propose this sort of interesting like model selection type problem where you train multiple UDA starts on different shift assumptions. You fine tune each one of these, and then you select kind of you know, the best one that performs best on some kind of small validation set. And what they show is that this is kind of nearly optimal without knowing a priori what the type of shift is. And so again, you have this kind of interesting model selection going on here, which I thought was quite cool. Okay, so just to briefly wrap up with some of my own thoughts. So I think this was already mentioned a couple times, so in the talk, and then also we had a question near the end on this. But yeah, I think it would be really interesting to see, okay, well, can you go beyond these linear structural causal models, but possibly incorporating nonlinearities. I mentioned here deep extensions. I don't know whether that's possible or not. I think the parametric form, linear form of the model seems to be important for the theory, but I think that would also be very interesting. A second kind of related question, which is, how robust are these methods to kind of model misspecifications? So, maybe if you do have a little bit of nonlinearity in the way that the structural causal models are formed, like how does that propagate to your in your risk bounds? And so I think characterizing that would also be quite interesting. So anyways, okay, so just to summarize, I think the key contributions here are these, so the structural causal models with the semi-supervised domain adaptation give us these minimax guarantees. We have these 3 different regimes for these structural causal models in terms of how we have the distribution shift between the source and the target. And then we also have methods that can account for lack of knowledge of the type of shift that we have. And so we have this kind of model selection type procedure. And so I think what's really interesting about the paper is that it kind of gives us a nice, crisp, clean setting to understand when few target labels suffice for doing this kind of adaptation. And so I think with that, I'll just end here, and happy to continue the discussion. So thank you.
Awesome, thank you. Yeah, Wooseok, do you want to respond?
Sure. Okay. First of all, thank you so much, Jason, for the very insightful questions, and it's very interesting to hear about some how other people think about our approach. And just going back to your questions, the first question was about the extensions to the nonlinear case or the deep extensions. I think I briefly answered this at the end of my talk, but I believe the one challenging part is that even for this unsupervised domain adaptation algorithms, so our method is based on this built on this upon this unsupervised domain adaptation algorithms. And although people use this like a deep neural net to learn some invariant features in practice, but indeed there is no theoretical guarantees. And even we actually UNC and I actually did some experiments, and they even fail under many different settings. So how can we design some UDA algorithms that can provably identify the invariant features? That might be the first step to go beyond the linear settings. And in terms of the second questions about the robustness under model misspecifications, I think this is a very interesting question, and I believe it's also quite challenging question. So currently, our theory it requires the precise model specifications, and if we don't have we have the model misspecifications, then we may not get the minimax optimal rate. So I'm not sure how we can make our fine-tuning strategies to be robust. Maybe one thought I can just come up with is whether we can just incorporate this distributional robustness approach to our fine-tuning, so that if we have some knowledge about how these target distributions, we have some vague information about how the target distribution change, but we don't have precise knowledge. Maybe we can somehow incorporate this distribution robustness approach to the fine-tuning. But I'm not sure if there is any better way, which is a very interesting research question we can think about. Yeah. Maybe you answer. Do you also have some other thoughts or?
Yeah, I think you covered You answered it very well. Yeah, I think yeah, it's the deep extensions is something we are trying to work on, but yeah, it's just doing theory is hard. But in practice, you can always try it and then do some kind of model selection on the target data set. Yeah, but I think that's what a lot of applied people do. They just get some intuition. They might not explicitly explain it with math, but they can get those intuition and try it on the label target data set. That I think makes also this semi-supervised domain adaptation is kind of more practical kind of setting.
Right.
Yeah.
Right.
Yeah.
I think just to add to that, I mean, one of the potential problems I can also see of working with something which is maybe too flexible is that you're going to lose that kind of, like causal interpretability, which, is obviously a lot more, it's a lot easier to understand when you have these kind of nice linear causal models. So I'm not sure if interpretability is a thing that matters in this area, but you'd probably lose that, I guess, if you went to something more complicated, like a deep model.
Yeah, I totally agree. Yes.
Cool. I also have a very quick question. So I asked Yuanzi in chat already. So this is essentially just about hybrid shift. So I could imagine that in the real world, it's probably not just one distribution shift, but it might be like a mix of different shifts, right? So you could think about sparse connectivity plus a confounder shift, or you could think about sparse connectivity plus a DRO style adversarial shift, or maybe even try to think about, covariate shift plus some of these shifts, whatever that means exactly, right? Do you have any thoughts, like whether your ideas can be extended to that setting, or like what you would like to see first there?
Yeah, that is a very interesting question. So I'm not sure if our fine-tuning algorithms can be sequentially combined together to address this the joint shift, where like you have let's say the sparse connectivity and the additive compounded interventions. Maybe you can first try to find some invariant features to address the compounded additive interventions, and then sequentially you also use some L1 sparse regression type algorithms to address the sparse connectivity perturbations. But I'm not sure how this actually works in theory. It's just my guess. We haven't really thought about this very seriously, but that's a very interesting question.
Sure. Thank you. Cool. All right. I think, yeah, we're, in 1 hour, so we're at time now. So yeah, let's quickly thank everyone again. Yeah, first thanks Wooseok for super interesting talk, and Jason for a cool, very interesting discussion. Thank you also, Yuanzi, for being here and answering the questions in Q&A. Thank you all for coming. Also, next week we're going to have Linbo Wang from the University of Toronto, who will talk about the synthetic instrument from sparse association to sparse causation. Thank you all for coming. I hope you have a great week, and see you next week.